This video was brought to you by our patrons on Patreon. If you'd like to join them in helping make more videos like these happen, check out the link in the description. Today we're going to look at what I think is a really interesting example of a functional differential equation. So by that I mean it's a combination of a functional equation and a differential equation. And this particular equation comes from the February 2013 Mathematics magazine. And so our final goal here will be to solve this equation f evaluated at 2x equals 2 times f of x times f prime of x, where we have this pseudo initial condition of f prime of 0 equals 1. But before we look at this main goal, we need some lemmas in order to help us along the way, one of which we will not prove and two of which we will prove. The first is maybe Cauchy's product formula for infinite series. So the sum as n goes from 1 to infinity of b sub n times the sum as n goes from 1 to infinity of c sub n is equal to the sum as n goes from 1 to infinity of this sum as k goes from 1 to n of bk c n minus k. So like I said, I won't prove that, but we'll just take that as a fact. And then we've got two binomial coefficient identities which we will prove. So let's start with this first one. So we want to look at the sum as k goes from 0 to n plus 1 of 2n plus 2 choose 2k. So this is the sum of the even indexed binomial coefficients. Okay, so the way I'll do this is using a bit of a trick. So I'm going to write this as 1/2 and then the sum as k goes from 0 up to 2n plus 2 of 1 plus -1 to the k, and then we'll have 2n plus 2 choose k. Now let's make an argument for why those are the same. So notice when k is odd, we have 1 plus -1, which is just 0. And then when k is even, we have 1 plus 1, which is 2. That'll cancel this half out here. So in fact, all that survives are the even terms. But after some re-indexing, we'll see that the even terms turn exactly into this. Okay, so that's why those two are the same. So now I'm going to split these into two sums, which is totally fine because this is a finite sum. I'll write this as 1/2, and then we have the sum as k goes from 0 up to 2n plus 2 of 2n plus 2 choose k times x to the k evaluated at x equals 1. So this 1 here I'm replacing with essentially 1 to the k, but I'm writing it as evaluation of this function. And then we'll do the same thing for the second sum. So I'll have plus 1/2, and then I have my sum as k goes from 0 up to 2n plus 2 of my same binomial coefficient, 2n plus 2 choose k, and then again x to the k, but now it's evaluated at x equals -1. So that would be represented by this kind of green underlining. But now we'll use the definition of what a binomial coefficient is, and that's a binomial expansion. So this gives us 1/2 and then 1 plus x to the power 2n plus 2 evaluated at x equals 1. So like I said, that's just by the definition of binomial coefficients. And then here we'll have 1/2 and then 1 plus x to the power 2n plus 2 evaluated at x equals -1. And now I think you can see where this is going. So evaluating this at -1 will simply give us 1 minus 1, which is 0. So this bit is all 0. And then evaluating at this at 1, we see that we get 1 plus 1 to the 2n plus 2. So we have 2n plus, or 2 to the 2n plus 2 over 2, which is 2 to the 2n plus 1. But that's exactly what we wanted over here. Okay, and now let's move on to this second one. So while this first one was the sum of the even indexed binomial coefficients, this second one is the sum of the odd indexed binomial coefficients. But now this is going to be fairly straightforward. Let's take 2 to the 2n plus 2, and let's rewrite it as the sum of all of the binomial coefficients, like we saw on the last calculation. So k equals 0 to 2n plus 2 of 2n plus 2 choose k. And now let's split this into even and odd parts. Okay, so splitting it into even parts will give us the k equals 0 to n plus 1 of 2n plus 2 choose 2k. So those are the even index terms, and then the odd index terms will be exactly our goal sum in this case. So the sum is k goes from 0 to n of 2n plus 2 choose 2k plus 1. Okay, so just to reiterate, these are the even ones and the odd ones. These are the even ones, and then those are the odd ones. But then by our first lemma, we know exactly what this is. So this is equal to 2 to the 2n plus 1, and then we have plus what is our goal sum. So I'll just rewrite that as our goal sum right there so I don't have to rewrite the whole thing. But that means our goal sum is exactly equal to 2 to the 2n plus 2 minus 2 to the 2n plus 1, because what we've done is we've constructed an equation for our goal sum. But we can factor a 2 to the 2n plus 1 out of that, leaving us with a 2 minus 1. But 2 minus 1 is equal to 1, and that leaves us exactly where we want, so we've established this. And now we're ready to move on to our main result. So let's maybe first note that this 2 times f of x times f prime of x is exactly the derivative of the function squared. So that's by the chain rule. So that's essentially what we will use here. Okay, and so now let's introduce some other notation as well. So let's set f of x equal to sum as n goes from 0 up to infinity of a sub n x to the n. So we're using a power series solution strategy here, which honestly shouldn't be a big surprise based off of this first bullet of the lemma that we did not prove. Okay. So now let's notice that the sum as n goes from 0 up to infinity of 2 to the n a sub n x to the n is equal to f evaluated at 2x. But then that's equal to the derivative with respect to x of f of x quantity squared, but that in turn is equal to the derivative with respect to x of the series we get using this Cauchy formula for the product. So let's see, rewriting that, we'll have the sum as n goes from 0 to infinity. So in my formula here, I wrote n starting at 1, but you could very similarly start at n equals 0. And then on the inside, we'll have the sum as k goes from 0 to n. And then next we'll have a sub k, a sub n minus k, and then we'll have x to the n. So notice we really have an x to the k term and an x to the n minus k term built in here, because those are parts of our b and our cn, but those will combine to this x to the n in all of the cases. Okay, but now we can take this derivative essentially just using the power rule. So that'll give us the sum as n goes from 0 up to infinity of n times the sum as k goes from 0 to n of ak a n minus k, and that's all multiplied by x to the n minus 1. But what we'd like to do in order to compare these two easily is re-index. So let's re-index here by sending n to n plus 1. So what will that do to our starting point? So instead of starting at n equals 0, we'll start at n equals 1 here, and likewise we'll start at k equals 1. So that'll leave me with the sum as n goes from 1 to infinity of n plus 1 times the sum as k goes from 1 to n of ak a n plus 1 minus k, and then that's all multiplied by x to the n. Okay, so that's looking good. And now let's quickly fix something. So let's maybe bring this down, and I'm gonna change it so it starts at n equals 1, and then we'll argue why we can do that. So we have 2 to the n, a sub n, x to the n. And then let's put a box around that because that'll be a fairly important formula. Actually, maybe the most important formula for this whole thing. And we can do this simplification here because a sub 0 must in fact be equal to 0. And how do we know that? Well, let's plug x equals 0 into the functional equation and see what happens. I guess I should say the functional differential equation. So that'll give us f of 0 equals 2 times f of 0 times f prime of 0. But f prime of 0 is 1. That leaves us with the equation f of 0 equals 2f of 0. But the only number that is twice itself is 0. So we have f of 0 is 0. But f of 0 is a sub 0 in this case. So that means that we could have started this at n equals 1 in the first place. Okay, so now let's extract coefficients, and that'll be the recursion which we'll use from here on out. So for n bigger than or equal to 1, we have the following. 2n a sub n is equal to n plus 1 times the sum as k goes from 1 to n of aka n plus 1 minus k. Okay, so now let's bring that up and then we'll get to solving this recursion.
Do you love what my team and I do to produce free math content? Then you should join the Patreon. For just $5 per month, about the cost of a cup of coffee, you can get ad-free versions of every video, access to the live seminar series, and more. Plus, you'll be helping keep the second channel, Math Major, where I post full courses on topics ad-free. If you're feeling extra generous, $10 a month gets you everything at the $5 level, plus you also get your name in the end credits of every video. We appreciate any support, but we ask you only join if you're financially secure enough to do so comfortably. Thank you so much, and I hope to see you there.
So on the last board, we constructed the following recursion after we assumed this power series solution. And now here I've just done a bunch of calculations and I want to go over them. So, and that is looking at this recursion for different values of n to get a guess on some sort of general structure for our coefficients a sub n. So let's look at the n equals 1 case. So in the n equals 1 case, this recursion simplifies to 2a1 equals 2a1 squared, which obviously implies that a1 squared is a1, but that has exactly two solutions. a1 is 0 or a1 is 1. But remember, we assumed that f prime of 0 was 1 and f prime of 0 is exactly a1, so that means we have to take this this a1 equals 1 as the value for this coefficient. Okay, so now let's look at n equals 2. So in that case, this recursion reduces to 4 times a2, that's 2 to the 2 obviously, equals 3 a1a2 plus a2a1. Now using the fact that a1 is 1, this right hand side simplifies to 6a2. But if 4a2 equals 6a2, that means that a2 is equal to 0. Okay, so we know a0 is 0 and a2 is also 0. Now let's look at n equals 3. So now the recursion simplifies to 8a3 equals 4 a1a3 plus a2 squared plus a3a1. Now since a2 squared is 0, that'll just simplify to 8a3 because a1 is 1. But that gives us the equation 8a3 equals 8a3, so it looks like a3 is a free variable. And now if a3 is bigger than or equal to 0, then we're able to express a3 as capital A squared over 3 factorial. And so I've included the 3 factorial in there in the denominator to make everything work out nicely. But then if it's bigger than or equal to 0, we can always express it as a square. That's why I've included this square here. Again, that's just going to make everything work out nicely as well. So this is sort of looking ahead and bringing back information from the future. Now, what happens if A3 is less than 0? Well, in that case, you need to do something fairly similar, but it'll be the same sort of idea. You would set A3 equal to negative A squared over 3 factorial and see what happens. I'll let you work out those details on your own. Now, let's look at this n equals 4 case. So in this case, our recursion simplifies to 16A4. And then we have 5, A1, A4, A2, A3, A3, A2, and A4, A1. Well, we know that A2 is 0, so that makes this thing and this thing 0. Simplifying everything to 16A4 equals 10A4, which means A4 is 0. So we've got A0, A2, and A4 are 0. It's looking like all of the even terms are 0. Now let's look at the n equals 5 case. So in this case, the recursion simplifies to 32A5 equals 6, A1, A5, A2, A4, A3 squared, A4, A2, A5, A1. Now these are 0, and then we can build an equation for A5. So I left out some details here, but it's fairly simple. You just build an equation for A5 using the fact that you know what A3 is. And you'll get that A5 is a to the 4th over 5 factorial when all is said and done. But looking at A3 and A5, along with maybe a new version for A1 as a to the 0 over 1 factorial, you'll see that all of these odd terms, including A1, seem to satisfy this rule down here that I have in blue, which is A2n plus 1 equals capital A to the 2n over 2n plus 1 factorial. Okay, so now I'm going to prove these closed forms using induction on the next board. Okay, so now let's get the closed form for those coefficients using induction, starting with the even indexed terms. So I've written that as a claim. So for all n bigger than or equal to 0, A2n is equal to 0. So our base case is done because we've already done the calculation. We actually have done more than we need for the base case. We know that A0, A2, and A4 are all 0. Now let's do our induction step, starting with the induction hypothesis. So we'll use a strong induction hypothesis. So let's suppose for all 2m from the set 0, 2, 4 up to 2k, we have A2m is equal to 0. And now let's look at A2k plus 2 using our recursion. So we have 2 to the power 2k plus 2 times A sub 2k plus 2 is equal to, let's see, this will be 2k plus 3. Because, like I said, we're replacing n here with 2k plus 2, the next even term, times, let's see, we have A1, A2k plus 2, and then plus A2, A2k plus 1, plus everything down to A2k plus 1, A2, and then plus A2k plus 2, A1. But now let's notice that everything in here in the middle includes as one of its factors an even indexed term. So everything has an A sub even term. But that means that these are all equal to 0. So that means we have this immediate simplification of this. I guess I should say that those are even indexed terms between 2 and 2k. So notice there's the 2, and then the 2k will come next. It'll be A sub 3, A sub 2k, and so on and so forth. So those are all equal to 0. Okay, but now let's see what we have now. We've got this, which is simply the number 1. We have this a1 here, which is simply the number 1. So this turns into 4 times 2k plus 3 times a sub 2k plus 2. But now let's look at your equation here, and let's notice that this thing that I'm underlining in orange has more factors of 2 than this thing that I'm underlining in red, which is the right-hand side. So this has 2k plus 2 factors of 2, whereas this only has 2 factors of 2. But that means that the only way for those two to be equal are if this number right here, a2k plus 2 equals 0. So that means we have a2k plus 2 equals 0 as needed for this case. Okay, so let's include that up here so we know this for sure right now. We know a sub 2n is equal to 0 for all possible n. Okay, so now let's move on to the odd claim. So to round out our odd index terms, we need to show for all n bigger than or equal to 0 that a sub 2n plus 2 equals capital A to the 2n over 2n plus 1 factorial. Again, we'll do this by induction. We've got more calculations than we need for the base case. As a reminder, we have a1 is capital A 0 over 1 factorial, a3 is capital A squared over 3 factorial, and we also showed that a5 is capital A to the 4th over 5 factorial. Now let's do our induction step. We'll start with an induction hypothesis. Let's suppose for all odd numbers, which I'll call 2m plus 1, from the set 1, 3, 5 up to 2k minus 1, we have a sub 2m plus 1 equals a to the 2m over 2m plus 1 factorial. So this is, again, a strong induction hypothesis. And now let's use our recursion to explore what a sub 2k plus 1 is. That'll be the next odd term outside of this set. So we have 2 to the 2k plus 1 times a sub 2k plus 1 will be equal to 2k plus 2 times this sort of sum right here. We have a1, a 2k plus 1 plus a2, a2k plus a3, a2k minus 1 plus all the way down to a2k plus 1, a1. So something like that. Okay, so now I'm going to rewrite this as follows. I'm going to rewrite this as 2k plus 2, and then notice I have 2 times a 2k plus 1. Those come from both of these terms using the fact that a1 is equal to 0. And then also I know that all of these even terms are 0. So that's every other term here, which means I'm only adding all of these odd things. So let's smush those all together into a sum. So that's going to be the sum as m goes from 3 up to 2k minus 1 over only the odd ones. So I'll just write a little odd down there to point out that I'm only going over the odd ones of am, and then let's see, it'll be a 2k plus 2 minus m when all is said and done. But now I'd like to apply the induction hypothesis to this. And I can do that, and that'll leave me with something of the following form. We'll have a to the 2k plus 2 in the numerator from the 2 capital A's that come from each of those. And then in my denominator, I'll have m factorial over 2k plus 2 minus m factorial. So something that looks like that. And now I'd like to re-index that so it looks a little bit closer to what we have over here. And notice I can do that as follows. So here I'll just bring this down, 2k plus 2, and then we have 2a sub 2k plus 1. And now this is going to turn into the sum as m goes from 1 up to k minus 1 of a sub 2k plus 2 over, let's see, we'll have 2m plus 1 factorial, and then multiplied by 2k minus 2m plus 1 factorial. Okay, so that's exactly the same as this sum right here where I've inserted these terms and then I've re-indexed to only include the odd terms. Okay, great. And I'm going to put some parentheses way over there. And now I'd like to fill this sum out so it starts at 0 and ends at k. So if I start this at 0 and end this at k, that means I have to subtract the 0th term and the kth term. Luckily, the 0th term and the kth term are the same thing, and that means I subtract 2a to the 2k plus 2 over 2k plus 2 factorial. Okay, good. So now let's bring this equation up to this spot and we'll finish this calculation off. All right, so here's a summary of what we had on the last board. I fixed a little bit of a typo where this exponent here should be 2k instead of 2k plus 1. And now I'd like to take this big sum and I'd like to multiply it by a certain version of 1. And it's a certain version of 1 so that we can use this over here. So I'll multiply the numerator by 2k plus 2 factorial. And then I'll also multiply the denominator by that, but I can bring that out front here. So I've got a 2k plus 2 factorial there as well. And now let's see what that leaves us with. I'll bring down a bunch of stuff really quickly. So I've got all of this. And then I'll also bring this a to the 2k out. And then that leaves me with the sum as m goes from 0 up to k of what's left over is in fact a binomial coefficient. It's 2k plus 2 choose 2m plus 1. So that's maybe like the biggest trick of this whole problem is to re-express the sum of these odd terms using this binomial coefficient setup so that we can use this binomial coefficient identity which we derived over there. So this is in fact, let's see, 2 to the 2k plus 1. So that gives us this nice equation right here. So let's write out this equation. So we have 2 to the 2k plus 1, a sub 2k plus 1 equals 2k plus 2 to a 2k plus 1, and then minus 2a 2k over 2k plus 1 factorial, and then plus 2 to the 2k plus 1 a 2k over 2k plus 2 factorial. That might seem a little bit gnarly, but actually it's fairly simple to solve this for a sub 2k. And I'll in fact let you do that. And you can see that all of the necessary powers of 2 will cancel. That's because we've got this power of 2 right here, the same power of 2 over here. So that's sort of how this trick works. So this will leave us with a 2k plus 1 equals capital A to the 2k over 2k plus 1 factorial, which is exactly what we need to finish this inductive proof, which means in fact we have a sub 2n plus 1 equals a to the 2n over 2n plus 1 factorial for all, natural numbers n, or non-negative integers n, maybe I should say. Okay, so now that we've got the formula for both of these types of coefficients, let's finish this off and see exactly what function we have. Okay, so finally putting this all together, we know that f of x will really just be the sum of the odd terms. So we have this sum as n goes from 0 to infinity of, let's see, a 2 to the power 2n over 2n plus 1 factorial times x to the 2n plus 1. Now I'm going to multiply and divide by a just to square this up. So we have the same power of a as we have x, and then we've got that same thing factorialed in the denominator. So rewriting this, we see that f of x is equal to 1 over a. So notice that this does not work if a is equal to 0, and we can actually branch off the case when a is equal to 0 immediately, and we'll see that we get f of x equals x. And that's one possible solution. So that's the a equals 0 solution, because notice every term maybe after a sub 1 cancels here. And you might say, well, I have 0 to the 0, but really we should have made that choice earlier and seen this happen. Okay, so now if a is strictly bigger than 0, that's the case that we're looking at down here. And that means we can divide by a. Okay, anyway, so that's going to give us the sum. N goes from 0 to infinity of a times x to the power 2n plus 1. I'll smush those together over 2n plus 1 factorial. But that's in fact a well-known function. That looks like some sort of version of the exponential function, but with only odd terms. But that's exactly the hyperbolic sine function. So we have f of x equals 1 over a times the hyperbolic sine of a times x. And that would be our nice final solution. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.